Sorry about the delay, guys. So today we'll do a little bit of a video lecture on just reintroducing the lab a little bit that we're hopefully going to be able to do tomorrow if we're in school. And then we will get into a little bit further into redox reactions and assigning oxidation numbers. There's Anders. Say hi to the chemistry class.
Hi.
So let me go back to the share screen and we'll just remind you of a couple things with the lab. So tomorrow, the hope is that we're in the lab, go right to lab A152, and we're doing the strong acid versus strong base titration. You guys will have to fill up these burettes. They're basically a volume measuring device that you will place the acid in the A marked side and the base in the B marked side. The acid is hydrochloric acid. The base is sodium hydroxide. Sodium hydroxide that you're working with, you'll need to take a peek at the stock bottles, the concentrations of the sodium hydroxide and ultimately the hydroxide will be probably right around 0.10 something or 0.100 something molar. Each station will be a little bit different. Okay, and then your job is to ultimately discover what is the concentration of the H plus ions using this reaction as we've discussed, right? And then you'll ultimately obtain the concentration of the hydrochloric acid, and that's our goal for tomorrow. We'll do a couple trials. The first trial, you go pretty slow on, take your time a little bit, and then the second trial you can go a little fast because you'll know a little bit more about how much base you got to add in for it to reach the equivalence point. So again, you'll take your another flask, you're going to add 10 milliliters of acid to the flask. You're going to add a couple drops of phenolphthalein. You'll add I can't remember the exact amount of water, but just to bulk up the volume of the liquid in here. It doesn't matter if you add some water to it. Doesn't change the amount of acid and H plus ions that are in the Erlenmeyer flask. And you'll switch it over to the base side and your Erlenmeyer flask, and you're going to add base until it swirls and turns pink. And I'll kind of show you what I mean by that so you guys have an idea on this video. Just sort of shows what you'll be doing when you're nearing the equivalence point. So sort of drop by drop, you're adding in the base, and then eventually it'll turn pink, and we hopefully want to have it even more of a faint pink color than that. Let me see if I can maybe get this back a little bit further. But you can kind of see as it's dropping in, the pink color is really holding quite a bit. That means you're getting close to the equivalence point. Early in the titration, you'll find that as you're just initially dropping it in, the pink will disappear quite readily and easily, okay? But as you're nearing the equivalence point, you'll see that pink kind of hold on. It may even turn a faint pink and you'll swirl it, and then eventually that pink color will disappear after a little bit of swirling. The other thing too to recommend is, like, if you're getting to that point, sometimes the base will splash up onto the side of the Erlenmeyer flask. I'll have some squirt bottles with some dehydrated water, some distilled water in it. Rinse down the sides to try to get the base down. Remember, adding the extra water doesn't do anything or won't affect your results. Okay? All right, so that's tomorrow. Let's go ahead and we'll go back to talking about a little bit more on redox reactions. Oops. Okay, so again, we kind of looked at this the other day. We did the demo with the zinc and hydrochloric acid. What was going on in that demo? Remember, Leo de Lange goes GR in an oxidation reaction. There's going to be a loss of electrons in oxidation, LEO. Gain of electrons. Gain of electrons is a reduction half reaction. So the reaction that we looked at was we took some zinc metal. We reacted with H plus ions from the strong acid, the hydrochloric acid. And we ended up with some zinc ions dissolved into that solution in the H2 gas, and that was the bubbles, the fizzing that you saw. ultimately these redox reactions can be split in what are called half equations. And we'll learn about how to write these and balance these later on. But again, in the oxidation half, we're looking at the substance that is being oxidized. Remember, Leo and Leo the Lion goes grr, loss of electrons. So zinc metal has no charge, but as is zinc plus 2 ion, it means it has lost 2 electrons. So that's the oxidation, the Leo part, loss of electrons, the oxidation half reaction. The reduction half reaction, the H plus ions from the hydrochloric acid, those H plus ions are being reduced because they are gaining electrons. So GER, G-E-R, gain of electrons is a reduction. 2 of these H plus ions combined with these 2 electrons to form H2 gas. So the kind of the quick sort of note here, and we said this the other day, is that you can't have oxidation without reduction. Oxidation provides electrons that are then going to be used by the reduction half reaction to create the full redox reaction. They're sort of embedded in both half reactions are obviously embedded in the full reaction, and you can't have one without the other. Okay? So some rules, you know, and some things that we've talked about. And by the way, guys, like as you're watching this, feel free to pause, rewind, whatever, go back. Oxidation and reduction occur together in the same reaction. You can't have one without the other. We just said that. There is no net change in the number of electrons in a redox oxidation half reaction. That's kind of hard to say. So in the oxidation half reaction, electrons are donated to the reduction half reaction. So like we saw on this previous slide, right? 2 electrons are produced in the oxidation half reaction. They're going to be used by the reduction half reaction. Okay. The ion or molecules or species that accepts the electron is called the oxidizing agent. So the species that donates the electron is called the reducing agent. So this one you got to put a little bit of your thinking hat on, thinking cap on a little bit. So from the previous example, the H plus ion is the oxidizing agent. So the hydrogen ion or ions, plural ions, they are the oxidizing agent. In other words, they bring about the oxidation of zinc. Okay? Zinc acts as the reducing agent. It furnishes electrons required to reduce H plus ions. So it furnishes electrons. Zinc is the reducing agent. Even though zinc is part of the, if I can get this to go back, zinc is part of the oxidation half reaction. It is the reducing agent because it provides electrons for the H plus ions, and vice versa. Hydrogen is the oxidizing agent that uses the electrons. Okay? So again, like I said, you got to kind of put your thinking hat on a little bit when you're saying this. Like the H plus ions are the oxidizing agent. They bring about the oxidation of zinc. Zinc acts as the reducing agent, furnishes electrons required to reduce H plus ions. By the way, and we'll talk a little bit about this, you know, why do they call it oxidation? And we'll talk about this some more later on. The fact is that oxidation a lot of times occurs in the presence of oxygen. Oxygen is a great oxidizing agent. It's not the only oxidizing agent, but it's an oxidizing agent. Okay? And then reduction, why do they call it reduction? You're reducing the number of particles or materials. If you look at like this equation right here, okay, there are a total of 2, 3, 4 particles, if you will. There's 2 ions and 2 electrons here. 4 particles here that are combining or reducing their number. They're reducing their number to only 1 single molecule, right? So the reduction half reaction is going to end up resulting in only a lesser amount, if you will, of particles or molecules, however you want to say it. Okay. All right. Next. So obviously we're in section 4.4. We want to look at how to assign oxidation numbers and talk a little about what those are. We're going to get you the rules set in place, and then I'm going to give you guys some homework for tomorrow. Oxidation numbers, basically, we said this the other day, they're kind of a form of electron bookkeeping. It allows us to be able to, in the reaction, be able to keep track of where the electrons are going and how we're going to be able to break this reaction up according to oxidation and reduction. Now, important note, your textbooks, pages 99 and 100, will have the rules and some examples. I'm sort of duplicating and adding to some of them in these notes that are coming up. But if you want a reference point to look at as you're going through these examples that I'm going to talk about, page 99 and 100 in your book is the example for the pages to access. All right. Excuse me. Rules wise, so the first rule, the oxidation number of an element. And so what we want to do is we want to be able to assign oxidation numbers to either elements or compounds or elements within compounds, I should say, the species within these redox reactions or potential redox reactions. Because then what it's going to allow us to do is to be able to assign these oxidation numbers and figure out what is the oxidation half reaction, what is the reduction half reaction, and is this even a redox reaction at all? Are electrons being exchanged within the reaction? So that's the sort of idea of assigning oxidation numbers and doing this electron bookkeeping method is why we're doing this. It's going to get us to be able to recognize, assign, and break apart into these half reactions, and then ultimately balance these equations. So this is kind of the first step. So rules-wise, the first rule, sorry, that was a little bit of a tangent there, but oxidation number of elements in an elementary substance is 0. So if it's an elementary substance, it could be like chlorine and chlorine gas, so Cl2, phosphorus in a P4 molecule, zinc metal. So we saw the zinc metal in the demo the other day. You know, think of copper metal or even the hydrogen gas, right, from the example that we looked at. In all of these cases, the oxidation number that would be assigned to either the chlorine and chlorine gas, the phosphorus and P4, zinc, copper, or the hydrogen in the H2 gas molecule, they would all have an oxidation number of 0. Okay, so that's the first rule. Come on, click open it. All right. Second rule is the oxidation number of an element in a monatomic ion is equal to the charge of that ion. So like sodium chloride can be broken apart into sodium and chloride ions. So the oxidation number is going to be the same as the charge of the ion. Okay? So sodium +1 ions has an oxidation number of +1. The chloride ion, which has a -1 charge, has an oxidation number of -1. Okay? Barium fluoride, another example, BAF2, that breaks apart into barium +2 and fluoride ions, 2 fluoride ions, right? So barium BAF2 is the formula that breaks apart into 2 fluoride ions. Each one of these fluoride ions has an oxidation number of -1, an oxidation number of -1. The barium +2 has an oxidation number of +2. Okay? So oxidation numbers for ions are the charge of the ion. If we're talking about oxidation numbers of ions in compounds, like this case, right, the oxidation number of each one of the fluorines are going to be -1, and then the barium is +2. You'll notice, and we'll talk about this rule a little bit more later on, that if there's a case where doesn't have an overall charge, the oxidation number of all of the ions or particles involved in the compound are going to add up to 0 because overall this has a charge of 0. We'll see that rule a little bit more later on in just a minute. Okay. Next rule, rule number 3, certain elements have the same oxidation number in all or almost all compounds they exist in. So group 1, they have an oxidation number of +1. Group 2 have an oxidation number of +2. Now, that kind of similar to this idea that we've presented to you about periodic table position and charge of ions. Same can be said. Group 17 has an oxidation number of -1. Group 16 has an oxidation number of -2. There are some exceptions, though. Again, hydrogen, right, is typically going to have an oxidation number of +1 based off of its periodic table position. However, like in this example, these two examples, there is such a thing as the hydride ion, the H-1 ion. Sometimes hydrogen can exist as a -1 ion. In this case, when it's existing within, say, these two example compounds that I have written here, it's as a -1 ion. Well, if it's a -1 ion based on our previous rule, it has an oxidation number of -1. Another one, oxygen is an example of one that's kind of funky. Oxygen based off a periodic table position is in group 16. So typically it's going to have an oxidation number of -2. But when it exists as the peroxide ion, okay, it has a charge of, the oxygen here has a charge of -2, okay. I'm sorry, the peroxide ion has 2 oxygen atoms in the ion, and it has an overall charge of -2. The oxidation numbers of both of these oxygen atoms have to be -1 each, because -1 plus a -1 equals -2. You're going to find out more about this rule in just a second. I said this just on the last slide too, is that the oxidation numbers of all the atoms have to add up to the overall charge, in this case, in this polyatomic ion. So in this case, the oxidation number of the individual oxygen atoms is -1, which is different than what it typically does. So a couple little sort of light bulbs that got to go off, hydrogen and oxygen sometimes, that we got to be careful of, okay? And then last, kind of as promised, I've sort of made allusions towards this last rule in the previous couple slides, but says the sum of the oxidation numbers in a neutral species is 0. In a polyatomic ion, it is equal to the charge of that polyatomic ion. And I kind of think of this as sort of pseudo charge assignment. You're not really assigning a charge, but pseudo kind of means fake, basically. I know I got dumb ways to remember things. This is just one of those ways that I kind of keep track in my mind. But here's an example. You're not really assigning a charge to the atom, but you're using sort of this idea about how in the previous couple rules, charge assignment designates oxidation number, okay? So pseudo charge assignment is that you're sort of assigning a charge, but really what you're doing is you're assigning the oxidation number as if it has a charge within that compound. All right, that might seem confusing, and it's okay. Let's just look at some examples, and I think that you guys will see that this is not terribly difficult. So here's an example of a molecule. We've got CH4. It's methane. It's natural gas, right? So it's the stuff that we burn in the Bunsen burners in lab. It's the stuff that's burning in your furnace at home, okay? We're trying to figure out the oxidation number of carbon. We don't have any of the rules that would tell us what the oxidation number of carbon is, right? None of the rules that I've given to you would assign the oxidation number of carbon. So we're trying to figure out what the oxidation number of carbon is. We know what the oxidation number of hydrogen is based off its position. It's got a +1 oxidation number. So we're going to set up this little algebra equation. X represents the oxidation number of the carbon. There are 4 atoms of hydrogen, each having an oxidation number of +1. Okay, so 4 times +1. We set this equal to the charge of the compound. Well, this compound doesn't have a charge. There is no charge. It's 0. Okay, there is no charge, so we set it equal to 0. Okay, so x plus 4 equals 0. Well, if x plus 4 equals 0, x has to equal -4. So the oxidation number of carbon in this compound is -4, okay? And carbon won't always have an oxidation number of -4, but in this compound, it has an oxidation number of -4. Second example, this is, I believe it's called the permanganate ion or permanganate polyatomic anion, MnO4-1. We're going to try to determine the oxidation number of the manganese here, okay? Because again, based off of its position in the periodic table, based off of any of the rules that we've given you before, we do not know what its oxidation number is. However, we do know what the oxidation number of the oxygen is, okay? This isn't the peroxide ion, it's not the funky peroxide, so oxygen has an oxidation number of -2 based off of its position in group 16 in the periodic table. So we are trying to figure out the oxidation number of manganese. X represents the oxidation number for manganese. -2 is the oxidation number of oxygen. There are 4 oxygens, right? So we take 4 times -2, okay? We set this all equal to the overall charge, in this case, of the polyatomic ion. the polyatomic ion has a -1 charge, so all of our oxidation numbers have to add up to -1. Okay? So if we add this together, so it's X plus -8 equals -1. What does X have to equal? Okay, or in order for this expression to be true, X has to equal +7, because a +7 and a -8 equals -1. +7 and a -8 equals -1. So in this molecule, I'm sorry, in this polyatomic ion, manganese has an oxidation number of +7. Manganese won't always have an oxidation number of +7, but in this particular polyatomic ion, it has an oxidation number of +7. Okay. All right. So here are your 3 homework assignments for tomorrow, or 3 homework problems for tomorrow. You're going to tell me the oxidation number for nitrogen within the ammonium ion. You're going to tell me the oxidation number for carbon, just a carbon atom, within the acetate ion. Okay. And then finally, you're going to tell me the oxidation number for carbon within the molecule C2H6, which would be ethane, I believe it is, ethane. So you're going to tell me the oxidation number for just nitrogen within this polyatomic ion called ammonium. You're telling me the oxidation number for carbon within the acetate polyatomic ion. And then you're going to tell me the oxidation number for a carbon atom within this molecule, C2H6. And the name of this molecule is, I believe it's ethane, if I'm not mistaken, if I'm good on my hydrocarbons. So that wraps up. Your 3 homework problems for tomorrow are right there. Do your work within your notebooks. We'll check those first things tomorrow, and we'll start with these 3 homework problems tomorrow. Thanks, guys, for listening. If you got any questions, obviously you guys can email me, and we'll try to talk you through it. And maybe if there's any questions, we'll start with those tomorrow after the video lecture. Other than that, 3 homework problems for tomorrow. Hopefully we'll see you guys tomorrow. See ya.